Yeah, good evening to all of you. Am I audible?
Good evening, sir. Yes, sir.
Yeah, all right. Last class we have started introducing Zener Diode, and in today's class we will look into the uh, applications of Zener Diode. Okay, so let's try to go into the details. Uh, this again textbook soft copy. I'm just making a presentation here. So let's start with Zener Diode applications, which is section 3.2 from the textbook. Basic Electronics by authored by Thomas Floyd. Okay, so let's go into the topic. As we already said, that Zener diode is basically a an alternate version of ordinary PN junction diode, but with a special manufacturing, with a lot of doping. The Zener diode has been manufactured, and its application is used. It can be used as a voltage regulator, especially when you want to have constant voltage, DC voltage across DC applications, especially the mobile application. It may be the laptop or it may be the smart TV, which demands DC voltage. Those applications, okay, across that, we need to have a Zener diode because that maintains a constant voltage across it. And it provides stable voltage, stable reference voltage. Reference means it's a DC voltage. And that is the main role of Zener diode as compared to the ordinary PN junction diode. So coming to the objective of this section, so Zener diode is basically used as a voltage regulation. That's we are going to describe that in more detail in today's class, and it's unless we are going to study that in more detail how to do regulation with variable input voltage when input voltage is changing. When I say variable input voltage can increase or decrease. We are looking, from both the angles. What happens when the input voltage is increased or decreased? How Zener diode performs its operation, and those aspects we are going to see in today's class. Then we are going to discuss Zener regulation with variable load. That is the next application of Zener diode, and Zener regulation from no load to the full load condition. No load means without connecting any load. That means resistance is made infinity, or the load resistance which we normally connect across the Zener diode. If we maintain constant voltage, if we make this as an infinite, then it becomes a no load condition. Okay, and we'll also see to how Zener diode performs its regulation operation when it is connected to the full load. So these are the two aspects we'll see, and finally we are going to discuss Zener limiting capability. So all these are the various applications that we can use Zener diode for various typical applications here. So first, let us start with applications such as Zener regulation with variable input voltage. Okay, so this is one of the important application of Zener diode. Whenever the input voltage is varying, still across output, Zener can maintain a constant voltage. Okay, in such kind of application, we're going to discuss right now. Okay, so let's go into the more details. Zener diode regulators can provide a reasonably constant DC level wherever you connect. If we have a regulator, Zener diode, if it is used as a regulator, and across its terminals, it provides a constant DC voltage at the output. But efficiency point, if you look at, there may not be significant, performance as Zener diode is going to provide. So we have to couple with other things so that it can provide a constant voltage across its terminals, and they're limited to the few applications, and that require only the low current to the load. In such kind of applications, it can provide a very good performance, but other than that, the performance is not so good from the Zener diode. And here are typical applications here. In the figure 3.9, we are going to illustrate how a Zener diode can be used to regulate a voltage across it. So let us see the figure 3.9. This is figure 3.9, and as you can see, here we have an experimental setup, which contains the a DC power supply. So which is the DC power supply, and this is the input voltage Vin, which is varying, and here we have an meter. This is an ammeter. Okay, so which measures current, and here we have an voltmeter. Okay, which measures voltage. So we have two instruments, measuring instruments. One is current measuring instrument, other one is voltage measuring instrument. So these two are connected. As we know that current instrument should be connected in series because it is an ammeter, and the voltage measuring instruments has to be connected in parallel so that it is connected across the Zener diode here. And here we have a DC supply which has got a lot of the variations in this DC supply. So this DC supply is not constant, of course, it is varying in nature, and that's why this arrow mark is given. So it is varying in nature. And when we say DC voltage is varying, accordingly the Vin also keeps varying, right? So when Vin keeps varying, let us see how it's affect across the output. So Zener diode typically comes with its, as we already mentioned in the last class, commercial Zener diodes are available with typical breakdown voltages, which we normally indicate as VZ, Zener voltage or breakdown voltage. Across its terminals, it tries to maintain the VZ, provided that it is not the current through this doesn't cross the limit. Okay, so IZK and IZM, we already mentioned in the previous class, lower current below which Zener diode doesn't perform regulation is IZK, and the upper limit is going to be the IZM, above which Zener diode doesn't perform the regulations. Only within these two limits, Zener diode performs its regulation operations here. So let us have a look at this how this when the input voltage is changing, when we have a lot of fluctuations in the input voltage. Corresponding fluctuations we can also see in the meter. Let's say, for example, specifically if input voltage is increasing, corresponding, the input current also starts increasing. IZ starts increasing. This is an example for as input voltage increases and current starts increasing. That is already shown here. This is an instrument which measures. Suppose if you give 10 volts here, then definitely this current is proportionally it increases. If I increase from 10 to say 15 volts, correspondingly current also will start increasing. That means the Vin and IZ are linearly they are increasing, and that changes can be seen through the resistor. If you consider a voltage drop across this, we can see that corresponding change in the voltage drop as input voltage changes. But the advantage here is we have connected a Zener diode which is in parallel to the input voltage. This maintains constant voltage irrespective of the changes or increase in the voltage, and that causes increase in the current. But here the changes in the voltage across its terminal is very small. So as you can see here, the changes in the voltage is it is a VZ plus delta VZ. Okay, VZ means the Zener diode which is meant for it. It's a breakdown voltage. And what we can see here is even though there's a big change in the input voltage, increase in the input voltage, I will give an example here, 10 volts to 15 volts change, just a typical example. And corresponding change in the voltage, what we see across it is very minute. So delta VZ is a small change that occurs because of a change in the voltage, but that is good. That's negligible, of course. And so we can say that the voltage across this is maintained as a VZ itself. Okay. So this happens only when the Zener current here, the current that is going here, flowing through the resistance, the current limiting resistance, if it is within this limit, IZK and IZM here. So this is an example of experimental setup which shows that if input voltage is increasing, there is a corresponding increase in the Zener current. And since Zener diode maintains its across its terminals voltage constant, so change in voltage is VZ plus delta VZ. So delta VZ is due to the increase in the voltage that may be quite small, and that can be neglected here. Okay, so this is the first experimental setup. Now let us move to the another setup where input voltage starts decreasing. Okay, look at this the experimental setup here. As the input voltage decreases, so this voltage we are taking an example here as decreasing. In earlier setup we have seen when input voltage is increasing, so we have seen the voltage across it remains constant. Okay, so it's VZ plus delta VZ. And let us see this experiment when input voltage is decreasing. So whether the output voltage is constant or not, we'll see that here. So in this example, they have taken as input voltage greater than VZ. Okay, so because to perform the Zener action, the input voltage cannot be less than VZ. So it has to be greater than the VZ. As we see that if you make it input voltage less than VZ, and definitely we are entering into the lower the knee region. So that is not allowed here. So in both the cases, in both the setup, So we should assume that input voltage is greater than the Vz. That means the applied voltage here is greater than the breakdown voltage. Okay, so that is the condition which we need to assume it before we set up this experiment. So when the input voltage is decreasing, corresponding decrease in the Zener current can be seen. It is mentioned here that Iz decreasing. So Iz means Zener current decreases because there is a decrease in the input voltage. These two are, that they are directly proportional according to the Ohm's law. It decreases, so therefore Iz also decreases. But now let us see that though the current through the resistance decreases, but let us see whether the voltage across the Zener diode can be maintained constant or not. So now we can see that the output voltage across this is Vz minus delta Vz. So whatever the changes is there, that can be subtracted from this Vz delta from the cut-in voltage because of the change in the decrease in the input voltage. So if you neglect this, the second term here, overall the voltage across the Zener diode remains constant. Still, it remains constant as a Vz. The conclusion here is very simple. When input voltage increases in the first experimental setup, or input voltage decreases in the second experimental setup, so corresponding increase in the input current can be seen in the ammeter. Okay, and here we can see the corresponding decrease in the current in the ammeter. But as long as the voltage, the current limit across the through the Zener diode is within this range. Okay, here we have a range here, so the voltage across the Zener diode remains constant. Okay, that's about the theory behind the variation of input voltage, and that provides Zener provides a constant voltage. Okay, it acts like a constant voltage regulator here. Okay, so now let's go to the commercial Zener diodes. Okay, so far whatever I've explained, it is already given in the this paragraph. I advise students to go through those paragraph and try to understand with more details which is given in this textbook. Okay, so now let us move to the next experimental setup here. How to measure the power levels and the limit. See the how the upper limit can be identified. Those aspects we can see with reference to Zener diode as a voltage regulator here. Okay. So to illustrate regulation operation, let's use the ideal model of this 1N4740A. This is going to be the Zener diode. Okay, so 4740A Zener diode. And since it is ideal model, we can ignore the Zener resistance. And here that's the model is given as shown in the figure here. IN means it is, sorry, 1N, not IN here. It is 1N4740. It is a silicon Zener diode here. So this is a commercial, okay, silicon Zener diode. Okay, 1N, N stands for here silicon. The letter, second letter here, N stands for silicon here. So 4740 is a number. A is given a number given by the manufacturer. So it's a commercially available Zener diode, and so this if we treat this as an ideal diode model, then in such case we have to ignore the resistance through this device. As we already said that voltage, the equivalent of Zener diode is a resistance and a power supply. So this is nothing but a cut-in voltage, and the resistance is forward resistance. In this case, it's going to be the reverse resistance. So this is the equivalent of a Zener diode. So now here, since it is ideal model, so Zener resistance can be neglected. And here we have a current limiting resistance. So I'm talking about Zener resistance, which is inbuilt within the Zener diode. And this is an external resistance connected to the Zener diode to limit the current flow through this device. And here we have an input voltage source, which is a variable voltage source. Okay, this is a DC voltage source, and we can vary this. We can increase or decrease this DC voltage source, and this is going to be the experimental setup. And let us try to measure the maximum, okay, the Zener current through this device. For that, we need to know what is the minimum current and maximum current. So this 1N4740A Zener diode, it has got IZK, okay, as 0.25 milliampere. Let me write it here. So for this particular diode, Zener diode, so IZK Zener current is going to be 0.25 milliampere. Okay, so it will be as per the data that is given here, and that represents the no load current. And the maximum current is not given on the data sheet. Generally, IZM, which is the maximum current. It is not given in the data sheet, though this is provided on the data sheet. No load Zener current is given, but maximum is not given. However, this can be calculated based on the power specification of a Zener diode, which is 1 watt. So 1 watt is the power specification given by the Zener diode for this particular Zener diode. So we can use the formula relating the uh, IZM, maximum Zener current, to the breakdown voltage Vz to the power dissipation across the Zener diode. So the maximum power dissipation is given as 1 watt for the Zener diode. Okay, so 1 watt by the this particular diode has got the breakdown voltage of 10 volts. So that gives me current as 100 milliampere. Though it is not given in the data sheet, but using power dissipation. Okay, so we can calculate the what is IZ, the maximum current. So maximum current, that is the Zener diode performs regulation, is 100 milliampere. So if the current is about 0.25 milliampere and below 100 milliampere, this particular Zener diode can perform its action. It can provide across these two terminals a voltage of 10 volts. Any current falling, a Zener current falling less than this. Okay, so if I is less than 0.25 milli, or I is greater than IZ, actually IZ, the current that is flowing here. Okay, so IZ, if it is uh, greater than 100 milliampere, then the Zener diode doesn't perform regulating action. Okay, so that should be noted while discussing this topic. Okay, all right. So we estimated for the commercial Zener diode 1N 4740A, Zener current is 0.25 milliampere, and maximum Zener current we have estimated here, which is going to be 100 milliampere. So the conclusion here is, as long as the current through the Zener diode remains within this range between 0.25 and 100 milliampere, the 1N4740A provides 10 volts as a voltage, constant voltage or stable voltage at the output. Okay. Now let us use this formula to calculate the other values. So for a minimum Zener current, the voltage across 220 ohm, this is the voltage across. Okay, the 220 ohm can be calculated. So for that we can use minimum Zener current. Of course, if I use IZK as Zener current, minimum Zener current, that gets multiplied with the R value. R value is 220 ohm, and the minimum Zener current is 0.25 milliampere. That gives me VR as 55 millivolt. Okay, now let us see corresponding change in uh, the voltage across the. This is actually the equation that relates voltage across the resistor. This is the voltage. So VR. Okay. So across this, the voltage is VR, and across this, the voltage is VZ. So across this, let me write it here, VZ. So you can apply KVL for this. That gives me minus V in. If I apply here, from here, minus V in, I'm going across the loop like this. Okay, so here the polarity is plus and minus, so it is a plus VR, and this is a plus VZ equals to 0. This is the KVL equation. I apply from here, ground, start with the ground, and I go in this loop through the resistance, and across the Zener diode, the voltage is VZ. So if you apply KVL, that gives me, this is by applying KVL across the loop, Kirchhoff voltage law for using for the loop shown, for the loop. Okay, this is a loop shown starting from the ground here all the way. Okay, so to ground here. So in this way we get minus V in, which is already shown here, plus VR, which we have here, and across this we have VZ, which is VZ is 10 volts. Of course, we have taken general value VZ, Then if we modify this equation, so this Vn is because I consider here as minimum Zener current that we have done here calculation with minimum Zener current. What is the Vr value? So Vr is known and Vz is known. From that we can calculate what is Vin minimum. So let us write Vin. This Vin I am making it as a Vin minimum. Okay, so that becomes equal to Vr plus Vz that is given here as you can see. Okay, so I showed just now how do we obtain this Vr is equal to Vin minus Vz applying the KVL, and if we rearrange this equation, we get it Vin minimum equals Vr plus Vz. Now we can substitute Vr is known already, which is 55 millivolt, and the Vz is 10 volts. So we get 10.055 volts. What do you mean by this? So what we have done here so far, let us go back and try to analyze it. So here we have taken Iz as Izk, minimum current we have assumed, and for that corresponding this voltage is known. The breakdown voltage is given as a 10 volts, and the input voltage, the minimum input voltage we have calculated. Okay, so which is going to be around 10.055 volts. That's going to be the input voltage, minimum input voltage. So let us calculate now the maximum the input voltage. Okay, for that I should use in place of Izk I must use Izm. That is the maximum current that is flowing through this loop in the circuit that is shown here. Instead of assuming here an Izk in the first case, we can assume as Izm. Izm. Here this is Izm. Okay, if I use Izm here, so then the voltage drop across Vr is going to be Izm times R. Izm is now we have calculated based on the power calculations, as you can see here. Based on power we calculated Izm is 100 milliampere. We'll reuse that Izm as 100 milliampere over here, and resistance is 220 ohms. Now we got to know the voltage drop across the resistance is 22 volts. So the voltage drop across this resistance is 22 volts. Okay, so for across 220 ohm is 22 volts. So that is the voltage drop across it, and now we can use same relation once again to calculate the maximum input voltage. Earlier we have called this Vin as Vin minimum when the Izk was flowing, but now we can call V in as V in max when Izm is flowing. So therefore this V in max equals now, if you rearrange it, it becomes Vr plus Vz. Vr is already known, which is 22 volts, and 10 volts is going to be the Vz. If we sum up together, it comes to around 32 volts. Now what we got to know is the V in can vary between V in above 10.055 volts, for which we got it from Izk current. Okay, this value what we got. Okay, this value, and it should be less than the 32 volts. 32 volts we got it because of Izm. Okay, and when the input voltage is between above 10 volts, 10.055 volts, and below 32 volts, so Zener can maintain provide constant voltage of 10 volts here. That's what it has been. We can conclude from the solving this relation from this problem. Okay. Any questions before we go on to the solving example problem of 3.5? All right, let's go and solve one example related to the topic that we have covered. So this example 3.5. So here let me read out the problem for you. Determine the minimum and maximum input voltages that can be regulated by the Zener diode in figure 3.11. So this is a figure 3.11 given, and here it is asked is to calculate minimum and maximum input voltages. Similar to the problem that we have solved, we need to calculate what is V in minimum and what is the V in max, which is the maximum input voltage that need to be that we can estimate it here, that can be regulated by the Zener diode. So in order to maintain output voltage as V out, okay, of this commercial Zener diode 1N4733A, so to what extent the input voltage can vary. So that means we should calculate what is the minimum input voltage and what is the maximum input voltage here. Okay, so let's work out and this problem. Let's go through the data sheet of this 1N4733A. This is a commercial Zener diode, and VZ of this is going to be 5.1 volt. Let me write it here. This value, as per the data sheet, okay, it is 5.1 volt. So this is the V out or VZ, whatever we call. So as per the data sheet, though it is not given in the problem, many times we should be familiar with what is the Zener diode and what is its cutting voltage. At least a few Zener diode, commercial Zener diodes, breakdown voltages, we must be aware of it. So in this example, so the it is already given to you. So VZ is 5.1 volt at IZ 49 milliampere, and the minimum current it is given as 1 milliampere, which is IZK, and Zener resistance is given, Zener impedance is given as 7 ohms at IZ. And for simplicity, we should assume this value ZZ over the range of current values, and also the equivalent circuit of that can be written. That is what we do in the next step. So now let us write the equivalent circuit of this Zener diode. So input voltage is retained as it is. We don't make any changes, and there is a current limiting resistor whose value is 100 ohm. That is also retained as it is. But in place of Zener diode, we have a resistance, Zener impedance, what we call. Its value is given as 7 ohms. Okay, so 7 ohms is Zener resistance, and the voltage is already given. It is 5.1 volt, which it can maintain 5.1 volt. And because of input voltage change here, so output voltage changes by 5.1 volt plus or minus Vz, delta Vz. Now we should calculate here what should be the V in minimum and V in max. So let's work out that similar to the previous example that we have shown. So IZK is as per the data given. IZK is the knee Zener current, which is given as 1 milliampere. And now we can use V out to calculate uh, this formula can be used here. V out is equal to this V out is equal to the 5.1 volt, which is the overall voltage across it, minus the delta Vz. The delta Vz is nothing but voltage across this. Okay, so delta Vz is in turn can be calculated by Iz minus Izk times Zz. So what is Iz and Izk? So Iz is the current that is flowing here. Okay, Iz minus Izk, we are subtracting this current here. So that Izk, and that's multiplied with the Zz resistance. Okay, so that gives me this equation, this internal equation. And now we can substitute all the values here. Vz is 5.1 volt, that is the Vz, minus Iz is given as 49 milliampere, of which this Vz is defined, minus Izk, which is given as 1 milliampere, and that's multiplied with Zener impedance, which is 7 ohms. If I substitute all these things, that gives me uh, the V out as 4.76 volts, and from this we can calculate what is the minimum input voltage, again using same relation that we have showed earlier. We have worked out for the ideal diode, but now it is an example with the practical diode. So we can use same relation that I showed here. Okay, so here you can see here this relation with the Vz is an ideal diode, but here we have a practical diode. So therefore the formula changes for the practical diode as Izk times R plus it is a V out, which we already worked out here, which is 4.76 volts. So now we can substitute Izk and R, that's drop across this resistance, and we already have output voltage across this, considering the practical diode as an example, that gives me 4.76, and if we simplify this, it gives me 4.86 volts. That is the minimum voltage that this supply can have. Okay, and to calculate the maximum voltage, one simple way is we can use even this power calculations. Let's now use that to find the maximum input voltage. First, calculate the maximum Zener current. Assume the temperature is 50 degrees Celsius or below, and from figure 3.7. So where is figure 3.7? This is 3.12, it seems. Figure 3.7 is previously shown, and the power dissipation is from that figure it is given as 1 watt. So from previously we already discussed about this. PD is 1 watt and VZ is 5.1 volt. IZM gives us 196 milliampere. That is the maximum current. If we know maximum current, then we can calculate what is the maximum input voltage that is allowed. Once again, we can use same output voltage for the maximum current now. So this is again VZ plus delta VZ. Delta VZ now becomes now IZM minus IZ. Okay, it is the difference of the current that goes through the Zener diode, and we have a ZZ which is about 7 ohms. Substituting all these values, that gives me V out as 6.13 volts. Okay, so for the maximum current of IZM. In turn, if you substitute in the V in max equation by considering drop across resistor and output voltage across Zener diode, uh, IZM is 196 milliampere and R is 100 ohm plus this V out is 6.13 volts. That gives us V in max as 25.7 volts. So we got to know that what is the minimum input voltage for the practical diode, which is 4.86 volts, and the maximum voltage input voltage of Zener diode for which output is maintained as VZ plus or minus delta VZ is 25.7 volts. Okay, so in this way the students can solve other problem related to this problem. We have one more problem here. Advise the students to solve those problems on their own. Okay, let's look at next application of Zener diode. So previously we have seen that effect of input voltage variations. Okay, how exactly the diode can maintain a constant output voltage, though there is a increase or decrease in the input voltage, and we estimated what is the minimum input voltage and maximum input voltage for which Zener can regulate and provide a constant DC voltage across its terminals. Now here we have another application wherein which we have Zener regulation with a variable load. Since in the earlier example we considered input voltage variation, but as you can see in this example, input voltage is fixed here. Let's not assume that this input voltage is varying, but what is varying is going to be the load here. Okay, so we have here load resistance connected here, and as you can see, there's an arrow. This variable arrow mark is given here that shows that RL is not fixed. It can be no load, it can be the full load. Okay, so that effect we can see in this example here. Figure 3.13 shows a Zener voltage regulator with a variable load resistor across the terminals. So here is an example with input voltage fixed, and there is a variation of load resistance across the Zener diode. The Zener diode maintains nearly constant voltage across RL. This particular RL, it maintains a constant voltage across it, since Zener diode, whatever the breakdown voltage that we have preferred, that same voltage is, we already discussed this. If the breakdown voltage is 5.1 volt, this across its terminals, the voltage will be 5.1 volt will be maintained. Since Zener diode and load resistance, they are parallel in nature here. So therefore, whatever the breakdown voltage that we select for the Zener diode, even across the load resistance, the same voltage is maintained, though there is a variation in the load resistance here. And this can be done effectively provided if it is a current flowing through the Zener diode, if it is beyond IZK and less than IZM. So same condition what we have said earlier, and that is applicable even for this circuit. In this example, as you can see here, there is a variable load connected. This is not a no load condition. This is a load connected for this across Zener diode. and if the Zener current is within this limit, then the voltage across it maintained is going to be the Vz, and there can be plus or minus, delta Vz here. So that we need to be aware of it. Okay, that is the Zener regulation with variable load, and with no load means we have to connect the Zener. I mean the resistance. We have to make it infinite. When the output terminals of the Zener regulator are open means it is an open circuit. There is no resistance here. The RL becomes equal to infinity. So the RL is infinity. The load current now, when the resistance becomes infinity, definitely the load current here this becomes zero, because no current will be flowing through this, and whatever the incoming current, the test current IT or whatever we call this, IT can be IZK, this can be IZM. Now complete current will be flowing through the Zener diode now. Okay, so let us read out that thing. Load current becomes zero, so IL becomes zero. There are two currents which IT will be providing as per this circuit. So one is going to be the IZ, which is a current leaving through the Zener diode, and there's another current called as IL. When RL is equal to infinity, then this complete current will becomes zero. IL becomes zero. This will go off, and only current IT now becomes equal to IZ. IZ. Okay. So and all of the current is going through the Zener, and this is a no load condition. So no load is connected here. That particular condition is called no load condition. When a load resistance RL is connected, a part of the total current is through Zener and a part through the RL. If at all, if you have a finite resistance of RL, then the current will branch out here. One will go through the Zener diode, and the other current will go through the IL. The current will branch out across these two branches. The total current R remains essentially constant as long as Zener is regulating. The total current here, what we say, IT, that remains essentially a constant one as long as Zener is within these two limits here. Okay. As RL is decreased, the load current IL increases. So if we decrease here, IL will start increasing. Okay. So because when the resistance drops here, definitely the load current is going to increase here when RL is decreased. Okay. So let us see both possible conditions here. Read out here, the total current R remains essentially constant as long as Zener is regulating. As RL is decreased, the load current IL increases. IZ decreases here. When this current increases, then IZ will be decreasing. So this IL will be increasing, provided if RL is decreasing. I'll write out here for you for your reference. So what is this RL? RL is decreased. When RL decreases, IL increases, because when the resistance drops, current through that increases. And what will happen to the IZ? IZ keeps decreases. Okay, because this current decreases. Okay, so total current IT should be maintained constant. IT will be maintained as a constant. Okay. Okay, so same thing we are seeing here. So IZ decreases. Zener diode continues to regulate the voltage until IZ reaches its minimum value as IZK. At this point, load current is maximum, and a full load condition exists. And there is an example here to illustrate that. Okay, so here we have an example here. So let me read out this example 3.6. In the example 3.6, we have determined the minimum and maximum load currents for which the Zener diode in figure 3.14. I'll show the 3.14 figure. This is a figure of 3.14 for this 3.6 problem. Will maintain regulation. What is the minimum value of RL that can be used? And here data given is VZ is 12 volts, IZK is 1 milliampere, IZM is 50 milliampere. Assume an ideal Zener diode where ZZ is 0, Zener impedance is 0, and VZ remains a constant of 12 volts. So VZ across this maintains a constant of 12 volts over the range of current values for the simplicity. I hope you understood the problem. We need to determine here the minimum and maximum load currents for which the Zener diode is in figure will maintain the regulation. So we need to calculate what is the minimum load current and maximum load current. Okay, in a simple way, I can say that we need to estimate what is the IL minimum and IL maximum load current. for which Zener diode maintains the regulations. Without compromising on the regulation, we need to estimate. Okay, so what should be the minimum load current and what is the maximum load current here. Okay, so let us go through the problem. Here we have a circuit diagram given. Input voltage is given as 24 volts. Current limiting resistance is given as 470 ohms, and IT is the total current that is labeled here. IZ is the Zener current that is going through the Zener diode, and IL is nothing but load current that is flowing through the load resistance here. We have a finite load. We will see for the two conditions with no load and full load. Let's assume that there is a no load condition of which RL is going to be infinity. If at all, if we make this as infinity, so what will be the load current? Load current becomes equal to 0. IL is 0. And IZ now becomes maximum and equal to the total current. This now, when this IL is going to be 0 because of RL is infinity. Now IT becomes equal to IZ. So IT becomes equal to IZ. So let us calculate IZ or IZ max now, for which we can equal to IT. We can substitute, subtract the at this point, which is V in, and this point it is VZ. IT total current is nothing but since current is not flowing through this branch should not be considered. Okay, so it is at this point we have an V in, and at this point we have VZ. So we have a resistance here is R, and I want to estimate IT here. This current is nothing but the voltage at this point minus voltage at this point divided by the resistance. So we have here formula for that, and now we can substitute. Input voltage is 24 volts given, and the Zener voltage is 12 volts, and resistance is 470 ohms. That gives me maximum Zener current as 25.5 milliampere. Okay, so this is the current maximum that is flowing when there is a infinite load resistance here. Okay. If RL is removed from the circuit, the load current is 0 ampere. Since IZ max is less than the IZM, 0 ampere is acceptable minimum value for IL. And because Zener diode can handle all of the 25.5 milliampere. So now let us calculate IL. IL minimum is going to be 0 ampere, for which the RL is going to be infinity for that. Okay. So the maximum value of IL occurs when IZ is minimum. So when IZ becomes equal to IZK, that is a condition of which the maximum value of IL will occur. So IL max now is equal to IT minus IZK. We can substitute here 25.5 milliampere, that is IT, that is total current, minus IZK is 1 milliampere, that gives us 24.5 milliampere, that is the IL max. So the minimum value of RL can be estimated if I know what is the IL max. So RL minimum is nothing but VZ by IL max. So 12 volts by 24.5, that gives me 490 ohm. Okay, so this is how, when RL is equal to infinity, what is the current we estimated, which is this current, and when RL is equal to minimum, okay, so the current is going to be the maximum, which is 24.5. So IL max is going to be 24.5 milliampere. So that's how we can estimate. So the conclusion here is, if RL is less than 490 ohms, RL will draw more of the total current away from the Zener, and IZ will be reduced below IZK, and this will cause Zener to lose a regulation effect. Regulation is maintained for only for any value of RL between 490 ohms and infinity. This is a 490 ohm and infinity. Lower resistance is this, and upper resistance is infinity. As long as we maintain resistance between 490 and infinity, the voltage across Zener diode is maintained constant. Okay. So that's the example, and there are a couple of related problems. I advise students to solve all those examples related to that, and let's have a look at another application of Zener diode as a voltage regulator, which is given here. This is a typical block diagram, okay, to provide a constant voltage across Zener diode, and this is a three-terminal voltage regulator. We have input voltage, output voltage, and there's a ground reference ground here. So now we can go for a block diagram level description of this one. Okay, so inside this we can visualize this sub blocks. So input voltage is now have a control element, and there is an error amplifier, and there is a feedback element here. And here we are not going to discuss the inner details of these subblocks, since we are discussing the Zener diode as a voltage regulator. It comes as an integrated circuit form, and it has got three terminals. One is ground, reference ground, and input voltage. We apply with reference to ground here, input voltage, and we measure output with reference to ground here, that is a V out. Okay, now this, since this is available in integrated circuit form, and its internal blocks are as shown here. Here we have a Zener diode and followed with a resistance, which is connected across it. Okay, so error amplifier will just calculate. Okay, so the error amplifier will have an input from the this Zener diode, and as well as the feedback element, and that will be fed to the control element. And again, this is works in this fashion. Okay, so this is how the block diagram. It is in a loop connected. This is a loop, as we can see here. Okay, so this is the internal block diagram of the voltage regulator here. So voltage regulator tries to maintain constant voltage across its terminals, even though there is a increase or decrease in the input voltage. Okay, so that's how the Zener diode performs the voltage regulations. Now, last application of this one is the Zener limiter. Okay, so very good application. The Zener diode can be used even as in clipping circuits, where we want to remove certain portion of the input signal. Suppose if I have a sinusoidal waveform, something like this, and I want to remove the voltage, say 3 volts and above. If I want to remove this, then I can use a clipper circuit to do that, and the output waveform that can be retained here is use different color so that you can visualize. I look forward to have output voltage in this way. I don't want to have voltage above 3 volts, and the output waveform is shown in green color like this. Okay, so this is a kind of waveform that I expect if I using a clipper circuit here. Now we'll see a different circuit, different Zener limiter circuits. Let us look at the first example here. So here we have a input sinusoidal which is applied here as an AC source, and here we have a Zener diode. And let us see that how it works for the positive half cycle and the negative half cycle. During the positive half cycle, okay, let us see the condition of the Zener diode. So there will be polarity with positive here and negative here. As we can see, as with this polarity, Zener becomes reverse biased. Zener diode is reverse biased. Now, how it functions? Okay, when the for the positive half cycle, when this part is considered, okay, so Zener diode becomes reverse biased. When Zener diode is reverse biased, so what happens when the positive half cycle comes here? So it maintains a voltage Vz across it, as you can see, till 0 all the way to Vz, because we know that Zener diode, when it is reverse biased, provides a constant voltage as a stable reference voltage as an output. So the stable voltage reference at the output of a Zener diode across this is it's going to be the Vz. Okay. As input signal keeps increasing, it will go up to Vz, and beyond that, it maintains a constant Vz. The voltage is not going to increase further above this. This is what happens in the positive half cycle. So we don't get any voltage after Vz. Suppose if Vz is going to be, say, 3 volts, so then the input signal rises to 3 volts here, and till that it maintains. After 3 volts, it won't rise, and it maintains a constant 3 volts. And now when the input drops, the output also drops. And this is what happens in the positive half cycle. And then in negative half cycle, polarity will change. So we'll have a minus here and plus here. So Zener diode becomes forward biased. When Zener diode becomes forward biased, the first quadrant comes into play. So Zener diode across its terminals maintains 0.7 volts, minus 0.7, because we are considering is a negative half cycle. Therefore, it maintains minus 0.7 volt as a reference voltage. Let's go through the second one, which is Again, another application. So here also we apply a sinusoidal AC source in this way. Okay, so let us analyze this in the positive and negative half cycle. For a positive half cycle, polarity will be plus here to the top and minus to the bottom. Zener diode is forward biased. So Zener diode, when it is forward biased, it maintains a 0.7 volt across it, and voltage signal will not rise above the sinusoidal wave will not rise above zero point 0.7 volts. And when the polarity changes for the negative half cycle, minus here and plus here, Zener diode becomes a reverse bias. Then in such case, the voltage will drop to minus Vz and it maintains minus Vz. Above this, it won't don't go above minus Vz. So this part is clipped here. Okay, this part is removed. Only we can see is minus Vz is maintained constant, and therefore the signal again turns back to the positive half cycle. It goes up to zero point 0.7 volt. In this way, this cycle will be continued like this. Okay, it goes up to minus Vz and again it goes to zero point 0.7 volt. So this is the second condition, second application of a Zener diode. And now we have here uh, another application where we have a two Zener diodes connected, namely Z1 and Z2. So let us use here Z1 and Z2. Okay, and let us analyze this circuit for positive and negative half cycle. For the positive half cycle, polarity will be plus here and the minus here. And among these two diodes, we can see that the upper diode is forward biased, and the lower one is going to be reverse biased. Okay, when the reverse biased, it maintains minus Vz2 here. So it is given a mistake here. So this has to be minus Vz2 minus zero point 0.7. That is the voltage that has to be maintained. Okay, for the negative half cycle. But for the positive half cycle, it goes up to Vz1. Okay, so it goes up to Vz1 uh, and zero point 0.7 volt is because this is reverse bias, right? This has to be Vz2, not Vz1. So this is reverse biased. So therefore, it has to be Vz2 plus zero point 0.7 volt is maintained here. When the negative half cycle comes here, for the negative half cycle, minus here and plus here. So the upper one will be the reverse biased. So this D1 will be reverse biased. D2 will be forward biased for negative half cycle. So this is correct. This need not be Vz2. The upper one has to be Vz2. That's all. And this is minus Vz1 minus zero point 0.7. That is the voltage, constant voltage level the negative half cycle can go. Though input is a complete cycle, but here to limit upper uh, part and lower part, we use Zener diodes. These type of circuits are called as Zener limiters, or you can call this shortly as clipping circuits or clippers, what we call shortly, or clippers. So these are the various applications of Zener diode. Okay, and we have one problem related to this, and by solving this problem, we'll try to end up today's class. So let's go through the example 3.8. Example 3.8, we need to determine the output voltage for each Zener limiting circuit in the figure 3.19. This is the figure 3.19. And two circuits are given here, namely A and B. So let us look into the figure A first. And here peak to peak, it is plus 10 volts is positive peak and the negative peak is minus 10 volts, and it is given to the this Zener limiting circuit. We are using here two Zener diodes. Let's look at for positive half cycle what happens. For the positive half cycle, polarity will be plus here and the minus here, and write the diode conditions here. So the upper diode is forward biased, lower diode is going to be reverse biased. So in that case, it maintains voltage 5.1 plus zero point 0.7 of this, because it is forward bias. Across this, voltage will be maintained as 0.7 volts. Therefore 5.1 plus zero point 0.7, it becomes 5.8 volt. You can see here the AC signal goes up to 5.8 volts, and thereafter it maintains a constant. And when the input signal drops, and the corresponding output also drops. And now let us look at what happens in the negative half cycle. This comes into negative half cycle. So just to remove it, negative half cycle, and see that how the circuit works in the negative half cycle. So the negative half cycle, polarity will be, we are considering this negative half cycle, polarity will be minus here and plus here. Okay, so upper diode, Zener diode is reverse biased, and the lower one is forward biased. And we know that for reverse bias diode Vz will be maintained 3.3, and for the forward bias diode 0.7 volt will be maintained across this 0.7 volt. So 3.3 plus zero point 0.7, which is going to be minus 4, because we are considering negative half cycle, therefore it goes to minus 4. So negative cycle of output goes up to minus 4 volts, and thereafter it maintains a constant. And let's have a look at the circuit shown in figure B. The only difference between the first and second circuit is Zener diodes terminals have been interchanged here, as you can see here. And now let us look at the positive and negative half cycle, how it works. Here the input voltage also, it is positive peak is 10 volts and negative peak is minus 20 volts. Positive peak is goes up to 20 volts. Let us see for positive half cycle how the diode performs. Positive half cycle polarity is plus here and minus here. The upper Zener diode now becomes reverse biased, and the lower Zener diode becomes now forward biased. Now, once the reverse bias 6.2 volt is maintained at the upper diode, across the upper diode, and lower diode 0.7 volt is maintained. So 6.2 plus zero point 0.7, that becomes 6.9. So the output voltage goes up to 6.9, and thereafter it maintains a constant. Okay. And when the negative half cycle is applied, the polarity becomes minus and plus here, and the upper diode becomes forward biased, and lower diode becomes reverse biased. 15 volt is maintained now. 15 plus zero point 0.7, it becomes 15.7. So input signal will drop to the level of minus 15.7 volts, and thereafter it maintains constant. And when input signal goes positive, the output also, corresponding output signal also goes positive. Okay. So with that, we have come to an end of Zener diode applications. And next class, I mean tomorrow's class, we are going to discuss uh, the applications, related to the, if any applications related to the Zener diodes are pending, we'll discuss that. Otherwise, we'll move on to the bipolar junction transistors. In tomorrow's class, we'll introduce bipolar junction transistor. Thank you all for watching this online video lecture. And if there are no doubts, I will try to wind up today's class. Thank you all.